Okay, so today we're going to be addressing exam 2. We're just going to be going over some general review tips to remember. And so I'm going to break exam 2 down into 3 parts. So the first part is NMR. The second part is reactions with epoxies. And the third part is a continuation of certain Grignard reactions. So we'll discuss all of these today. So let's start out with the NMR because I think that's what people remember the most because we've been doing NMR the whole time. So obviously we're using hydrogen NMR. So you're utilizing you're figuring out the number of hydrogens and how they're located to give you a hint of what the shape of a molecule looks like. So let's just take this example, and this is from the practice exam 2. It's question number 7, so the first NMR question. And can you guys hear me well? Because sometimes I've heard that like my speaker isn't that great. No? Okay, perfect. All right. So again, so you can use your IR spectrums as well, but we just prefer to really heavily depend on that HNMR for most of the information we need. So we're given a spectrum for the HNMR, and we're given several peaks, and this one is a 5 hydrogen multiplet, and then we're also given a 3 hydrogen singlet. We're also given a 2 hydrogen doublet, a 1 singlet, and then finally a 1 multiplet. So the first step in all these problems, especially if you have O's, is to kind of think about your degrees of unsaturation. So when we look at this one, I'll just remind you again of how we do degrees of saturation. So we're going to count all the carbons and all the hydrogens. And just remember that oxygen stands for 0 hydrogens. Some kind of halogen, so we denote that with X, stands for 1 hydrogen, and then N stands for minus 1 hydrogen. Okay. So with that in mind, we know that our oxygens aren't going to count at all. So we can go ahead. So we have C6H12 here. And so what's that equivalent to? Well, we need, in order for it to be 0 degrees of unsaturation, it would be CnH2n plus 2. So when we have 6, that would be C6H2 times 6, which is 12 plus 2, which is 14. So then by comparing these two to each other, we can tell that we're missing 2 hydrogens because instead of having 14, we have 2. And that means that's 1 degree of unsaturation. So with that 1 degree of unsaturation, what we're going to do is we're going to know that this has 1 double bond in it. And again, from your experience, you'll know that this is most likely a carbonyl group. So let's start off with drawing our structure. So usually the easiest place to start would be either like, I like to start with something that's 3. So we have a 3 singlet right there. So what could a 3 singlet look like? Well, a 3 singlet can either be attached to this many things, or it could be attached to like a double bond with one thing, or it could be attached directly to an O like this, but we don't know that so far. But actually looking at this, I know that one of the O's is going to be a carbonyl. The other O, what do you think it's going to be? You can either say it or you can send it in the chat. What do you think the other O is going to look like? If not a carbonyl, because we only have 1 carbonyl. There's a really important hint, and that is right here. And in this problem, you're not given the IR structure, but you don't need it so much. OH, yeah, exactly. So that's a sign of an OH. So we know that it's definitely not going to look like that. It could either be like this, or it could be like this, something like that, or it could just be like, yeah. So those are some of our options. Anyways, So we don't really know what it is yet, so I'm just going to leave that one singlet sitting there like that. So now that we've finished this part, I'm going to cross it out. And then let's move on to our the 5 multiplet. So a 5 multiplet is pretty tricky because there's no such thing as like 5 hydrogens all being in one spot, right? So we can tell that this is a multiplet that's made up of many different a few hydrogens in a few different spots, probably like a couple of different spots, because again, there's like no such thing as having, there's only like a maximum of pretty much 3 on one spot. And then if you have a multiple of 3, so if you have like 6, then you know that it could have looked like this because those are exactly the same thing. Or if you have 9, then you know it could have looked like this, right? It could have been like a chert. So in this situation, 5 doesn't really make any sense. So we know that it's on 2 different carbons. So let's start with that multiplet being, for example, so it would probably be here. So there would be a 3, there would be 3 hydrogens here, and then adjacent to that there would be a certain number of hydrogens, probably more hydrogens than less. And then we also need to find a spot for a 2. So to follow that, and I don't see any, there's a 2 doublet there, but there's no 2 quartet, so that might be part of the multiplet. Do you see that? Because like we only have, because like I know there's going to be like 2 hydrogens here, but we only have a 2 doublet there. We don't have anything, that 2 doublet wouldn't work. So this could be a 2 multiplet, especially if there's more hydrogens to the right of it, so that would make a lot of sense. So then continuing from there, we don't really know what's on the other side, what's on this side exactly, but we can now cross out the 5 multiplet. So now we need a 2 doublet and a 1 multiplet. So in order to make it a 1 multiplet, I'm thinking of putting my 1 multiplet in this position with the arrow right here, because that's the only thing that could fit, because you can't put a 1 singlet there. We know that's from the OH. And we can't put a 2 doublet there because it's already at least a triplet. So I'm going to put a 1 multiplet in that position. And probably this would be a good place to put our OH because we have 2 different spots and we don't know what to do with them. And so there goes our 1 singlet and our 2 doublet, or no, not our 2 doublet, our 1 multiplet. Now our 2 doublets, we can start bringing this over together. So how many carbons do we have? We have 6. We need 6. We have 1, 2, 3, 4, and 5. So if we just attach one more and make it like this, that would give us a total number of carbons. And we have to make this a 2 doublet, so it can't have anything to the right of it since it already has 1 to the left. So in that position, I'm just going to put my carbonyl. Yeah. Okay, yeah, this one works. So again, just to review, let me go in a different color. So let's call this A, B, C, D, and E. So A is this right here and this right here. Oh, sorry. Both of these things together, they make up A. Because they're so close to each other, they just get like kind of jumbled up like that. And then we have our 1 multiplet right there. So this is E. And then we have a 2 doublet, which is C, and then finally our 3 singlet, which is B. Okay, so that's just a quick review, and then let's go do one more NMR problem. And this is the second NMR problem from the exam, and then we'll just move on because there's I'm pretty sure that most people are really good with the NMR already. If you're having issues, then just let me know. And also you can just send like solutions of what you have anytime you want, and I'll take a look at it. But so this next one is C6H14O, and it has a 3 triplets, a 6 singlets, a 2 triplets, a 2 triplets, a 2 sextets, and a 1 singlet. So this one does have an IR spectrum with it, and like as you guys know, the IR spectrum for the OH is pretty clear. So it does include an OH peak in there. So we know that this is an OH. Okay. So let's just do our degrees of unsaturation just to check. So 6 times 2 plus 2 is 14. So we know that there's 0 degrees of unsaturation here. So we can just go ahead and get started. So I'm going to start with the 3 triplet because that's like such a classic pattern that we all know. So there's 3 hydrogens there, and adjacent to it there's 2 hydrogens, and that's what makes it a triplet. But that 2, so this one's taken care of, right? But that 2 triplet, actually I don't know how to, I'll cross it out below. That 2 right there, it has 2 options. It could either be the 2 sextet or the 2 triplet. Well, we already know it can't be the 2 triplet because it has 3 adjacent, which would make it a quartet at least. So we're going to go and say that it's a sextet. So knowing that it's a sextet, we know that it has to have 5 adjacent hydrogens altogether. So that means this is a 2 as well. You know what I mean? Because you add the 2 and you add the 3 together, that's 5. You add 1 more because that's how our NMR works, and that's 6. So that's a sextet. So this one is also taken care of. Now this 2 that we just wrote in there, that one must be this 2 triplet right here. And that means that since it's already a triplet from these 2 hydrogens adjacent to it, it must come to an end here. What kind of end can it come to? We know that it's not going to come to this kind of end because we don't have an oxygen available for that. We know it can't come to this kind of end because there is no double bond in our thing. So it must come to the end that is kind of like a tert structure, which is where it goes like this. Okay. And we just need to figure out what these are. So from here, we can see that we have our 6 singlet, which is actually really good because if we leave 3 hydrogens on each of these, those are 6 singlets, right, altogether. There's 6 of them, and they're all singlets because adjacent, there's no hydrogens. So then that just leaves, so we cross that out, so that just leaves our OH right here from the 1 singlet. So when you look at this structure, and we're going to call this A, B, C, D, and E, A is this right here. B is going to, or sorry, this is going to be D, which is a 2 sextet. And then this one's going to be C, a 2 triplet. And then these 2 together are going to both compose B, which is a 6 singlet. And then finally this part is E, which is a 1 singlet. Okay, so yeah, so I guess just to review, something very important. Oh, and then let me just give a quick review about when you have a aromatic ring. So when you have an aromatic ring, what you can expect is you can expect something between 7 and 8, okay? So you should always look in that area and see if you have something there. So if you do have something there, you either might see something that looks like this, or you might see something that looks like this. 2 peaks, essentially. And so what does the 2 peaks mean? These are 4 hydrogens altogether, meaning that the aromatic ring is substituted on 2 points. And we just always do them para when we're doing our working out. And then if you see them with 5, this would be 5 hydrogens. If you see it with 5 hydrogens, that means that there are 5 hydrogens available in the aromatic ring, which makes it only substituted by 1 thing. So that's really important to think about. And so that's tip number 1. And tip number 2 that I have, which is really important, is when you come to a stopping point. So let's say that in this situation, let's say this was a 3 triplet. So then we know there's 2 hydrogens here. But let's say that this 2 hydrogens was a 2 quartet. So that means that we can't have any hydrogens on that next carbon. or that next onto the left side of it. So what does that mean? So there's a few options, and I'm going to draw them all out. So the options are that there is like an oxygen it's kind of like shaped like that, or it could be that there's a carbonyl and something coming off, or it could be that there is just 3 substituents off of that area. Or the last important one to remember is that that could actually be the place where it attaches back onto an aromatic ring. So I think these are all the options I can think of that we typically do. So just keep these in mind for if you have if you have this and it's a free singlet right here, well then we know that there can't be anything right here. So you have to choose one of these options. How do you choose these options? So the aromatic ring one is like, do you have an aromatic ring in your IR spectrum, in your NMR spectrum? If so, then it might be a ring. But if you have any double bonds, it could be a carbonyl. If you have any oxygens that are not double bonds and not OHs, it's most definitely going to be like this. Or if really none of those other options work, then you might want to try this out. Okay. So I think that's it for all the information I have on NMR. Let's move on to our epoxy questions. Does anyone know where he had that really nice chart that like it like kind of like showed like all the different epoxy reactions that you can produce? It was really cool. Oh, here it is. I found it. Okay. So if you go to the March 4th lecture and go all the way down to lecture notes, then you will find a really nice sheet that explains everything you need to know about epoxies. And we'll talk about that now. So in terms of reactions for epoxies, there are 8. 4 of them are acidic and 4 of them are basic. And we're going to review the basic pattern that you can just memorize. Okay. So let's talk about acidic ones first. So in terms of acidic ones, and the model we're going to be using is this. Why are we using this model? Because it shows clearly that there's less hydrogens on this side and more hydrogens on this side. Or you could say less substituents on this side, more substituents on this side. Either way you want to think about it, that asymmetry is important for illustrating the difference between acidic reactions and basic reactions with an epoxy. So if we react this with the first acidic one, which is HBr, we get the Br going to the place with the least hydrogens. So the OH is here and the Br is here. And how does this happen? So you can think of it as if a Br was attacking that carbon, and then that broke that bond, and that grabbed an OH, okay? So you can think of it like that from now on. So that's with HBr, which is clearly acidic. Then we have H3o plus. H3o plus would just be the addition of an OH. So we get an OH. Clearly this is going to be the new OH, but that's besides the point. We get 2 OHs in that spot. And then there would be the addition. In this case, this is a phenol with an alcohol. So you can write this you could write it like this. OH, or you could write it as, you might see it written as this, or you might see it written as PHOH. And pH just stands for phenol. And then in the bottom of that, there's H3O plus, which is the part that makes it acidic. So what happens here is, again, the phenol with the OH goes to, oops, that's not good, goes to the left side, or the side with the least amount of hydrogens. And then finally, the last of our 4 acidic reactions is something like this maybe, and that is also an H3O plus, and this one gives you the same thing as above, pretty much. I don't really know why they're like that, but yeah, it gives you the same thing as above. It attacks on the side with the least hydrogens. So all of these are acidic. You either have HBr, which is clearly a strong acid that we always use. H3O plus is in all the rest of them. And as for those ones with OH, they're actually not really like considered bases. If you think about it, like usually when we're doing organic chemistry, our base is the one that has like a negative charge on it, right? Okay, so those are the acidic reactions. Let's go on to the basic reactions. So for basic reactions, our first one is NaOCH3. NaOCH3, why is this significant? Because this is the conjugate base of the above question. So when you have the acid, it goes to the side with the least hydrogens. When you have the conjugate base of that same thing, it goes to the side with the most hydrogens. So here, what we're going to get is we're going to get our OH on this side, and the OCH3 is on the other side. So it's kind of like very similar to the question right above it. It just really illustrates. Obviously, like if you don't know, this is a spectator ion, so this is just O minus, which is the base, right? And this can be in HOCH3, or let me turn that around. CH3OH. It can be that kind of solution, but as long as the base is there, that's what makes it basic. Next, then we have a very similar one to above, and this one is Mgx and H3o plus. So in this case, when you take away the Mg and X, what does it give you? It gives you a base, right? So even though it might be in an acidic solution, just like here, it might be in an acidic, a slightly acidic solution. This one's even in a strong acid, but this, in the end of the day, it's the phenol with a negative charge. So it is a base. It needs to accept a hydrogen. It wants to accept a hydrogen. So here again, the OH ends up being on the left side, and then our phenol is on the right. Okay. And this is different from the above question where we added a phenol, because the above question there was an O there. So it was phenol OH. This bottom one is just phenol MgX, which is phenol with a negative charge. And then after that we have, do you guys have any questions so far? I'm not seeing any, but just send them if you have any questions. Next we have LAH and H2O. And this one is just going to add a hydrogen to the right side. How do we know that this one is basic? Well, LAH is just an H minus that attacks, right? And again, since it's an H minus, it's kind of basically a base. So if you have LAH, it's a base, and it will go to, the hydrogen will go to the right, to the side with the most hydrogens. And then finally, we have NH3, which when we do NH3, it attaches an NH2 to the basic position. Okay, so these are all of our basic reactions. Those are all acidic reactions across the board. If you see an acidic reaction, it's going to go to the thing that you're adding, the substituent you're adding goes to the side with the least hydrogens. If it's basic, the substituent you're adding goes to the side with the most hydrogens. So that's a basic rule you can memorize. And we also should talk about how you can form these epoxies to even go about these reactions in the first place. So let me find some questions. Okay, so one of the basic ways that you can remember how to do this, there's a few, but one of the ways to do it is to take a let me just, okay, here. So you can take like a chain, for example, that has a it can have like a Br and an OH, yeah. Br and an OH. And you take that and then all you have to do is react it with NaOH and H2O, and that gives you an epoxy across the area where those two were. So it has to be an epoxy that covers the distance between the Br and the OH. Obviously, the Br and the OH need to be conjugated for this to work. What else? There is a way to break the epoxy as well. So the ways to break the epoxy are pretty much what we just talked about above. These are all and then epoxide. And then so that's how to break an epoxide, and then this is how to form. So that's one of the methods right there. There's actually a few more methods. I just need to find them. One of the ones that I remember a lot is if you have a double bond. This is from Orgo 1. If you have a double bond, all you have to do is like CH3O3, or sorry, CH3 CO3H, and what that'll do is it'll give you that epoxy right there, which is cool. And what else do we have? I'm trying to figure out more methods of formation. Can you guys think of anything else? I think that might be it. Yeah, I think that's it. So now that we've talked about formation of them, there's one more thing we need to talk about, which is there's just a few more reactions we need to know. So after you have an epoxy, you can actually use here, let me draw this out. You can use HClO4 to break that up and just cause a little bit more stereo specificity. Okay. So this one adds two OHs that are cis to each other. But if you want two OHs that are, sorry, they're trans to each other. If you want two OHs that are cis to each other, all you have to do is take the double bond, and straight from a double bond, you're going to use OSO4, and that gives you two cis OHs in those positions. So again, this is the syn and this is the anti, and you'll want to keep that in mind for your retrosynthesis. Okay, that's pretty much everything I can think of with regards to the epoxides. I'm just going to look through the exam for if I've missed anything else. Oh, yeah. So when it comes to the epoxides, and also something else, we're going to talk about this as well. But we learned about experiments to do with dense hydrogens, so D2O instead of H2O, or LAD instead of LAH. So we're essentially replacing it with a marked hydrogen, a hydrogen that's easier to recognize because it's dense. So we have 2 minutes left quickly before the break, but I'll just go ahead and explain really quickly. So in this situation where we talked about it just a second ago, and we're reacting this with LAD, for example, and that will be in H2O, what happens is that the D is the part that attacks. So this produces a D minus, right? And that D minus will come and it will attack, oops, wrong side. It'll attack this side because this side is the side with the most hydrogens, because this is basic. So what happens is that we get this. We get the OH here and then the D here. And so why am I bringing this up? Because these are the experiments that you might not remember, but essentially the D comes from here, and this H that okay. So the H that attacks the actual double bond or the actual carbonyl or whatever it is we're talking about comes from the LAH itself. The H that we get on the oxygen comes from the water or the solution. So that's because a D specifically attacked this carbon, but then this oxygen is just going to grab whatever is surrounding it in solution. And in this case, it's using, in this case, it's using H2O instead of D2O. So that's why we have an H in that position and a D in that position. And I really urge you to, you know, definitely like think about these and try to be very comfortable with this concept because it'll probably come up. And so another application for this is when they have a carbonyl that's being attacked by LH or NAB, what is that thing? The dissolving metal that you can use instead? Yeah, NAB4. Yes, exactly. So no, NABH4. Yeah. So there's LAH and then there's NABH4. And so that 4 can be changed to a D. So you can use NABD4 or you can use LAD. Okay? So those are your options for the Ds that can be used to actually attack. And then the solution could be a D2O, but in this case it's not. Okay, so with that, I'm just gonna go ahead and we're gonna pause. All right, so let's continue back of where we left off. So we were talking about how when you have LAH or NABH4, those can be substituted with Ds and use them as a marker to figure out where the hydrogen from each side is going. And so you have to be familiar with those experiments. So that kind of ends that section about the epoxides. And so from here, I just want to go on to finish up some other things about related to Grignard reactions or related to carbonyls, I guess. And then from there, I'll just do a couple of retrosynthesis questions and we'll be done. So in terms of the carbonyl reactions that I want you to know, obviously there's the one with a carbonyl like this, something like that, and when you react that with LAH, there is an H minus that will attack from here, and so what we get is this OH. Now, again, if we were to label it, so this is usually inside of like H2O or something. So if we had the same situation, but it was LAD and H2O, we would have a D here and an OH here. And then if it was the same situation, we're just changing it up one more time. And this time it was LAH and it was the H2O that was D2O in this situation. Then we would see an H in this position and a D up here. So that would be OD. And yeah, so some other situations with these carbonyls. So like LAH, which you should know, LAH reacts with, let me see, I'm trying to remember the rules for this. So LA, because I don't want to say anything that's wrong. So LAH is more reactive, I think. So LAH is good enough to work with here. LAH is good enough to work with acids, or no, let's go ahead. Ketones. ketones, aldehydes, acids, and esters, whereas NABH4 is only good enough for ketones and aldehydes. So use that information. So that information, I think, is this exam. So basically, you're going to use that information to figure out what reacts with what. So like, for example, in the above case, this is a ketone and it's reacting with LAH, so it will be reactive. But there's multiple situations, obviously. So here's another situation where we have this and it's reacting with LAD, and H2O. And so in this situation, LAD is able to react with this. This is an ester. So it will react, and what will happen is that we'll have a D- come and attack here, and that will break this off, and then another one will come and it will attack. So what we end up with, is we have our OH there, because it picked up an H from the H2O, and then there's two Ds attached to that, because those are the Ds that came from the LAD. And then we also are going to have, all the way on the other side, we're going to have an OH. And this OH has picked up its H from the H2O. Okay. Yeah. And so sometimes you're going to be left with some weird products. So let's do this example, which is important. So in this situation, we have a slight asymmetry, where you'll notice that on this side, the carbonyl comes first, and on this side, the carbonyl comes second. And so what does this do? Well, when we react this with LAH, what happens is that the from this side, an H is going to attack, and it's going to cut this off. And from this side, the H is going to attack here and cut this off. So what we end up with is, I'm going to draw it right below to make it more clear, but we end up with this on one side, and then we end up with this on the other side. And that's what creates the asymmetry there, because we cut it off. And then we'll also have an additional OH here and an additional OH here from the parts that got cut off. Okay. And I think that's it that I wanted to talk about in terms of that kind of stuff. Here's an interesting one. So, so we also need to remember our ester formation stuff for this exam. So when it comes to ester formation, there's a few different ways of doing it. So you can either have like some OHs that react together, and that will just give you like this. So you can have OHs reacting together, or you can actually have an OH and an Na and a Br reacting together. So you can have something like this, OH, and then plus, or react that with Na and a Br. And what that will do is it will give us the same thing. So those are two different methods of forming an ester. We also have, actually that's well, these are actually ethers. So then an ester formation would just be like the same thing, but you just have to include like a carbonyl there or a carbonyl here or something like that, you know. And then yeah. So here's a question that's asking you about where something came from. So we have a pentane on this side. Okay, we have a hexane on that side. So what happens is that we have to figure out where this came from. So we need to figure out it says what is the alcohol and what is the acid that this was formed from. So what it has to be is that it necessarily has to have the acid on this side, and it'll be like this. And then on the other side, it's just an O, or an OH, more specifically, that is attached to the pentane. So that's how to figure that one out. And then PPC is a reagent that we used here. So PPC is a reagent we learned about, and all PPC does is it takes an OH like this and turns it into a carbonyl. Yeah, and I think that's all for the majority of our reactions. So now I just want to go on and finish up with some retrosynthesis problems. So here are some retrosynthesis again from the practice exam. So we're starting off with that with a toluene, and that becomes this very long, complicated structure with an ester on it. So for this, we're going to have to figure out how to kind of end up attaching pretty much everything in this square on. So one of the best ways to probably do this would be to do a Grignard first, because if we did a Grignard, then we could end up attaching an oxide in this position, and then at that point it would be a simple matter of reacting it with this. So, but there are multiple ways to do this. You could choose to do the method here, which is to have an OH and a Br. But I'm going to use a different method. So first we're going to do NBS, and NBS is just going to attach a Br to the benzylic position. And then we'll just do Mg and Et2O, and that will give us that turned into an MgBr. Then from there, we're going to do our Grignard. So our Grignard is, we want to make this into a, I kind of want to add a OH to this position. So what I'll do is I'll add one more carbon, on the other side we'll have a hydrogen, and so one more carbon, that's all I need. And also on that, there's just going to be a double bond. Oh, a ketone. This has to be reacted with H3o plus. That gives us, oh, this is wrong. So that gives us, it gives us this. And then from there, all we have to do is we can do Jones to turn that into an acid. So if you remember the difference between PCC and Jones when it's primary, so Jones will take a primary alcohol and it'll turn it into a acid. And PCC will take a primary alcohol and turn it into an aldehyde, essentially. Okay. When it comes to secondary, they're both the same. So secondary alcohols will just both be converted into a carbonyl. So we draw our answer for what happens after Jones, which is that we get this acid. And then from there, it's just a matter of taking this OH and forming it together into an ester. Okay, and then let's just do one more. Actually, we'll do two more. I'll choose one from the bonus problems to make it a little bit more complicated. Okay, so here's one more that looks interesting. So this one starts off with a double bond, and it ends with a carbonyl instead. So what we're going to have to do is we're going to have to figure out how to attach everything from here. This carbon is a part of the original structure. So to do that, I'm thinking to do a Grignard reaction. And so for that to happen, we need to be able to add a Br to that position. So how are we going to do that? We're going to use, we can either do, we have a few options for that one. We can either do HBr, but make it like, what do you call it? Anti-Markovnikov. So in the bottom you can have H2O2 or something like that to make it this, like this. Or you can also go a little bit more like a roundabout way if you don't remember that. You could just take this and you could go with turn it into an OH and then from there go to a Br. And so the way for that is B2A6 and H2O2. And then that will give you an OH in that position. And then from there, you just do PBr3 and that will give you that turned into a Br. But I think this way is much faster, HBr and H2O2. And so then at that point, we're just going to change that to an MgBr. So that would be MgET2O, and we have MgBr there now. And then we just have to react it with the Grignard that we want. So the Grignard we want has to include 2 carbons. Wait a second. This is actually looking a little wrong. Okay, I'll have to check back on this one. So this is a question that is on page 4 of the practice exam for exam 2. So I'll have to check in about this one, and I will send a message to the group when I find out what's going on here, because it appears like something is pretty wrong here. But in the answer key. But if I were to just continue from here, because now I know that what I'm doing is wrong, I would probably react this with something like this, right? And so that would get me here. And then from there, I would have to kind of remove this OH and get it back to this position, which is really the tricky part. So honestly, I think there might have been a mistake with this problem because it does not look correct. So I'll just move on and I'll send the answer to that in the chat. Because the way that it is done in the answer key is that the person went ahead and did, they did something like this. Yeah, so they attached something like this. And what would really happen in this situation is that you would get this. And that is one too many carbons. And so there's no way to really go from here back to here without messing everything up. So that's why the answer key is flawed. And so I'll just bring that up when I figure it out. So going back to the final retrosynthesis problem today. So for this problem, which is actually really tricky, we go from a plain benzene ring to a benzene ring with this off of it. And so how are we going to do that? This is really complicated because we have to be able to attach that whole chain on. So probably the best way to start would be to do Br2 and FeBr3 because that's the only way of attaching something really onto a ring that would be helpful for us. So that gives us a Br in the desired position. After that, we can go ahead and change this to an MgBr, and that'll give us this. Then from that position, we'll have to go ahead and do a Grignard. We'll actually have to do almost like 2 steps here, because the first step is going to be to include 1 more carbon, and then from that point we're going to have to do, because if you look at this, the carbons that I colored red, they look like they could have been part of an epoxy. And if we get, like, if we make this part a base that attacks the epoxy, it would be a base, so it would go to the side with the most hydrogens, which is kind of what we want right there. So it kind of looks like that would be the best approach for this, which is why first I need to get it so that we have, like, the only way to get this as a base and attack it is if this is MgBr, because then it'll be a base and it'll attack the right side of the left side of the epoxy. So from this MgBr, we're going to just extend it by 1 carbon because that is necessary. So how are we going to do that? We're going to do a Grignard with 1 carbon and H3o plus, and that'll give us this. And then from there, all we have to do is do PBr3 and MgET2O. So I'm going to do that all in the same step. So in the top, I'm going to have PBr3. And then in the bottom, I'm going to have MgET2O. And so what that'll do is it'll give us MgET2O. And so that'll just give us all in one step so that we don't have to worry about writing too much. It'll give us an MgBr in this position. So then from here, all we have to do is use this with the epoxy to get the answer that we want. So the epoxy is just going to be, to draw it in the same orientation, it's going to be like this. And yeah, so what's going to happen is that this is essentially a negative charge, so I'll redraw it. So we kind of are coming at it with this, and this is just going to attack here, and that is the answer that we get, which is the correct answer. So that was a little bit more complicated. Just keep in mind certain principles, like the idea that especially in your bonus questions, you may have to do multiple steps, so either multiple Grignards or multiple epoxy steps. Yeah, so I think that's it for today. In terms of everything else, this is definitely not like a complete review of exam 2, but I haven't really received any specific questions or anything, so obviously you need to go back and you need to really like study exam 2. So as for all your exam prep, you should do both exam 2, the practice exam 2, and then you should also do all 4 quizzes. So your 2 actual quizzes and then the 2 practice quizzes. And honestly, if you do all those, you should be fine. Obviously, that's just for exam 2. So you should do, in all, you should be doing around 6 exams, redoing or practicing from 6 exams, and then about 12 quizzes altogether. And if you do all that, you'll be totally fine. And then there's also the new material, which we'll be going over next week once we finish reviewing for the final. Okay, so I'll let you go there and see you next time.